All right, we're live. All right, so at this point, we've pretty well tackled everything in chapters 2 and 3. So exam 1 is going to be coming up soon. I think that my plan is to have it go live on Thursday and be due Friday night at the end of the day. I might have it go if I can get it finished before then. I might have it go live like Wednesday night at midnight, so you have all day Thursday and all day Friday. I'm going to try to give you about 48 hours to tackle this. Um, the way the exam is going to look, it's going to be a 2 hour long exam. So once you start it, you've got 2 hours to do it before it logs you out. So do bear in mind that it is timed. Uh, the We'll talk about the security measures and how I keep you guys honest later this week. I still have to do kind of a dry run tech test for some of the stuff to make sure that I know how it's going to look both on my end and on your end to make sure that things are straightforward, but there may be some tech requirements that I'll talk about later. But that's coming up by the end of the week. Before I move on to chapter 4, which is not going to be covered on the exam, the exam was going to cover just the stuff we've done for the last 2 weeks. Are there any questions about homeworks that you guys are puzzled with from the chapter 2 or chapter 3 homeworks? Because otherwise we're moving on. So
the only question I have is that can we get like more examples to like maybe do like between now and between the tests, so like kind of like a study guide kind of thing.
So I generally don't do like I'm not going to give you like a sample test or anything, but I can at least sort of break down the sorts of things that I expect you guys to be able to do. So let's do that real quick. So not the right camera. There we go. So when it comes to like chapter 1 and the 1D kinematics, there's several concepts that you guys have to be familiar with, right? Obviously, you need to know about all your kinematic variables, position, velocity, acceleration. You should know what those terms mean. You should also know the distinction between velocity and speed. They're similar, but they're not the same. You should know the difference between displacement and distance. So, obviously these are related to position, but they're not identical. So you should know the terminology, be fluent with that, be very clear about the distinctions, because part of your success or failure is going to come from recognizing, the nuance in how something is asked. But probably the biggest part of that is going to be solving kinematics problems. What are those kinematics problems going to look like? Well, for me, I have like 3 broad categories. I have what I call the plug and chug problems. Now, what do I mean by those? These are the problems where once you break them down, getting the answer basically boils down to identifying what thing you're solving for out of your 6 kinematic variables and what things you don't know but don't care about, and finding that one equation of motion that you can plug stuff into and solve for. And it generally just takes you, that one step. So the simplest problems tended to be the plug and chug problems. Obviously, because they're the simplest, they're probably, not the most numerous on an exam. I tend to sort of go up about a level in complexity for those. But these are the ones that you do basically one step. You find one equation, you rearrange it, solve your one variable, and you're done. Probably more important are the more complex questions. And there's a couple of examples of types of more complex questions. They're what I call multi-stage problems. right? So multi-stage problems are problems you're going to have to break down into sections. And you're going to know these when you see them because something in the problem tells you that the acceleration is different at different points. So look for problems where there's multiple accelerations. Now, what do I mean by multiple accelerations? The problem on your homework where you had the train going from one station to the other, right? In that problem, there was a portion of the ride where the train was speeding up, so it had one acceleration. There was a portion of the problem where the train was traveling at a constant speed, so it had a zero acceleration. And then there was another portion of the ride where the train was slowing down, it had a negative acceleration. So, in order to solve that problem, you had to not just do one inventory, you had to do three separate inventories and break them all up. There was a problem we did in class where we had an elevator ascending to the top floor. So it was speeding up part of the time and slowing down part of the time. So you had to break it into two parts. There was another homework problem where you had a rocket ship taking off. And for the first 30 seconds, the rocket ship has one acceleration, but then the engine's cut off. And after the engine's cut off, it has a different acceleration. And so each of those problems were multi-stage problems. You had to take the bigger problem and break it down into little mini plug and chug problems. So this became sort of a series of these simpler problems that you had to do in sequence. And so that's a lot more representative of the kind of stuff that I'll throw at you on an exam, because it definitely tends to weed out the people who really get it from the people who just kind of sort of get that they have to plug things into an equation. It's harder to get it correct if you're just kind of flailing about than it is one of these. The other big sort of complicating factor that you might have to deal with are what I call multi-object problems. This is where you have multiple objects that are all moving around. All right, examples of those that we've seen. We did the velociraptor question in class where you had the velociraptor chasing you and you had to figure out where it caught you. There was a problem on your homework where you've got two cars. One of them is traveling faster behind the other car. And so you got to figure out like how much this guy has to accelerate by to not crash into the other guy. So in order to solve that problem, you had to track the motion of both cars as they moved. The Deadpool problem in the homework where Deadpool is falling down, but the van is traveling sideways, and you got to have them arrive at the same point at the same time. So the thing about these multi-object problems is that you have to do one inventory for each object. And then something about the problem is going to connect one inventory to the other. So for instance, in the Deadpool problem, the time that Deadpool was falling for had to be the same amount of time that the van was traveling for. So the time for those two inventories had to be the same. And that was what allowed you to combine the two things together to solve them. The Velociraptor question. The thing that was in common was at some point, both the person and the velociraptor were going to be in the same location at the same time, and that's when the velociraptor eats the person. So both the position and the time for those two inventories had to be the same. And what made those problems more complicated is that in order to solve them, you ended up having to generate one equation for one inventory, another equation for the other inventory, and then algebraically combine them. And the trick there was rather than look for things that exclude everything you don't know, you wanted to find equations of motion that included the things that those two inventories have in common. So you'd end up with two equations, but two unknowns. And so that's definitely something you should be prepared to solve uh, as part of this exam. The last thing from chapter 2 that I tend to maybe put a little bit of emphasis on is graph interpretation. Physicists love graphs. So this is the kind of stuff that you were doing during that moving man lab that first week, or I think there's a couple of problems on your homework. There's like one where you had to figure out the instantaneous velocity. So being able to interpret what you're being told by a graph of something's position versus time, or velocity versus time, or acceleration versus time. If I ask you to, write me what the graph would look like for an object in a problem, that's something you should be prepared to do. And the big thing to remember from each of those is that if you've got a position versus time graph, the slope of that graph is the velocity. If you've got a velocity versus time graph, the slope of that graph is equal to the acceleration. And being able to connect those various things, probably pretty important. And I would probably be remiss if I didn't suggest that for like the fifth thing on that chapter 2 section of the exam, you should definitely know the distinction between average versus instantaneous. We certainly spent a little time on it. You had a couple of problems on your homework where you had to calculate the average velocity for something. And the trick there is that if you're looking at, say, the velocity, for instance, the average velocity is just how far you went divided by how long it took. And if I'm looking for the average velocity, I can't simply just take all the different speeds I have and average them. That doesn't work because it's this. This is the definition. So
Can you show 4 again when you're done?
Yeah, absolutely, absolutely. So if you're solving a problem like this, you have to figure out, well, how far did the object travel in total, and then divide by that time. The instantaneous velocity happens when the time that you're measuring for shrinks down and becomes infinitesimally small. And so the instantaneous velocity, if you're like, say, looking at a graph of position versus time, the instantaneous velocity ends up being the slope of a tangent line at any given moment. Because what's happening is you're shrinking down the delta t until the time interval shrinks to infinitely small, and that's where that starts to come together. So I'd be remiss if I didn't include at least something with regards to that somewhere on your exam. So is that better? You missed that?
Yes.
Cool. So in terms of chapter 2 stuff, that's kind of my checklist of things to see if you understand.
Okay.
So I usually write the exam with that kind of stuff in mind. Then in terms of chapter 3, we add a couple more wrinkles to the mix here. So for chapter 3, the big thing there is we have vectors. Right? You should know how to deal with vectors, and there's lots of things you should know how to do with vectors. If I give you a vector in magnitude and direction form, you should be able to break it down into components. Right? You should be comfortable taking a vector. If I say that I have an object that's traveling 30 meters per second in a direction of 30 degrees north of west, you should be able to break that down into an x and a y component pretty easily. You should also, if I give you a vector in component form, you should be able to tell me a magnitude and direction. Right? I'll definitely expect you to be able to do that. So if I say, hey, I've got a vector that's 3i hat plus 4j hat, you should be able to figure out, aha, that vector has a magnitude of 5 units and it points in a direction of 33 degrees above the horizontal, right? You should be able to figure that out. You should also be able to add vectors or subtract vectors. because I'll definitely expect you to demonstrate that skill. That's going to be important because it's going to continue to happen through the next several chapters, right? It's not going to go away. Even next semester, we're going to be adding and subtracting vectors a lot. So all of these things are not just important for chapter 3, they're important for physics in general. So those are straight up vector operations. Then we also learned how to do kinematics with vectors. So that's what we call projectile motion. Which is basically where you apply two-dimensional kinematics and vector operations at the same time. And that's the stuff we were doing on Thursday of last week. So, when it comes down to what that exam is going to look like, this is my checklist of things. And I want to make sure that at least somewhere on that exam, I'm forcing you to demonstrate a mastery of each of those things. Where is this going to come from, what that's going to look like. Think about all the problems on your homework where you kick a football in the air and you figure out how high it goes or how far it goes or what velocity it has when it hits the ground and that kind of stuff. Any number of those. The vast majority of homework for chapter 3 is going to be stuff from this category. So even though I'm writing one thing, it's a huge thing. It's a thing that's going to be a really, really big deal. So put a star around that. That's like super important. But that's sort of my checklist of where I expect you to go. Now, as far as like extra, like if you're looking for extra examples, right, or extra work for this kind of stuff, I'll kind of point you in the direction of where to find that kind of stuff. This is sort of how I used to prep for exams back when I took this stuff as a student. So if you're prepping for a professor's exam, the first thing you should do is you should look at the homework problems that professor assigned you, right? Because they didn't just pick those problems at random. Each of those problems was something that the professor saw and they said, man, that's a thing I want my students to be able to do. So if there's a problem that I put on the homework, you should make sure you know how to solve it. I would start with those. Hopefully you've done all those homeworks. What I used to do when I was prepping was I'd look back over the homework assignments. And what I would try to do is I'd try to solve that problem cold. So I'd open up that problem. I wouldn't look at what I turned in before because just reading over my old solutions doesn't help me. It's super easy to waste time doing that. But I'd try to see if I could start that problem and work through that problem from start to finish without having to look anything up or check my notes. If I got stuck, I'd go back and look at my solution from before and say, oh yeah, that's where I made that substitution. That was pretty clever. Yay, put it away and try it again. So I would do that until I was comfortable with those sorts of problems, right? If I had time left over after looking through the old homework problems, then what I would do is I'd look at the back of the book where there's problems in every chapter. And I'd try to find, actually, skip that. Before I looked at the back of the book, I'd look in the text of the chapter for worked examples. And the reason I do that is because the solutions are right there. They're in the textbook. So I would look at those questions and I'd try to solve those cold. I'd read the question part, but I would ignore all the explanation and try to do it myself. If I got stuck, I'd go back and I'd look at that question to see where they did something I didn't remember to do, or they noticed some pattern that hadn't been obvious to me. And I'd work those through. Then if I still had some extra time, and you probably will because your book doesn't have a whole lot of worked examples, it's kind of not the best book in that regard. Then what I would do is I'd look in the back of each chapter and I look at all the homework problems that my professor didn't assign. And I would see if I could find problems that were similar, or at least seemed similar to things that he assigned, but maybe like slightly different twists. And I will point something out to you. This is something that I don't see a lot of students make use of, and it's really unfortunate. Doggone it, it's not the right screen share, stupid. Let's try that again. to the thing. There we go. All right. All right. So let's say I go to, here's your physics textbook, right? And here is chapter 3. And I'll go to problems and exercises, right? So some of these problems actually became problems that I used in the homework, but others that were not. I would look at some of these and ask myself, do I know how to solve them? Like, here's question 5. Could I solve this problem? This is not super different from one of your homeworks, but it's not exactly the same. Could you solve that problem? Notice when you do this, you can see like which section of the book it's coming from. It's from section 3.2. So if I get stuck on it, I can always immediately go back and check out that section to see if maybe that will help me. The other thing I will point out is that if you go to openstacks.com, where the textbook is, and you go to student resources, one of the things in the student resources is the student solutions guide. And it works out not all of the problems, but quite a few of the problems. So what I would do, come on, is, all right, here's, I look at the student solutions manual and I say, aha, problem, or section 2.3, number 14, I know they worked that problem out. So what I might do then is go back to that. Don't look at the solution yet, because that doesn't help you. Try to work it out, but if you get stuck, you can always unstick yourself by looking at that. And I might preferentially try to work some of those as examples, because by doing that, I'm going to build the confidence that I know what I'm doing. And there's plenty of additional examples of things to play around with. So if I was, prepping for this exam and I had extra time left over, that's where I would look next. I would look at all those problems that are in that textbook that I didn't assign you, but for which I already know I had solutions, so that if I'm stuck, I can then try to unstick myself and I can tell where I'm screwing up. Does that kind of give you a sense of where to start?
Yes.
Yeah.
Yeah, that's what I used to do. I've seen a lot of students who, when I ask them, like, I've had students who've come in and they've been just wrecked by my exam. They come through and they do terrible. And
Yeah.
I'll pull them aside after the exam and ask, well, what was your study regimen? And a lot of them will tell me things like, oh, I went on Khan Academy and I watched a lot of videos. And that's really, really popular these days as a study method. And there's nothing wrong with Khan Academy. By all means, watch those videos. It's great. You can watch the class videos from this class, but just watching someone do like problems on a video is the worst way to prepare for an exam, right? It used to happen to me when I was a kid, and I was a pretty bright guy. I was pretty good at this stuff. I mean, that's why I majored in it, right? And so what happened to me my freshman and sophomore year is I was this cocky kid who thought he was super smart, and I'd sit in class and I'd pay attention and I'd watch the professor solve all kinds of problems. I'm sorry? I think he's talking to someone else. All right, I'm going to mute her real quick. So I would go through all sorts of problems and, watch my professor solve these problems. And every time he's solving a problem in class, he'd be like, oh, I get that, I get that, I get that. And that all makes perfect sense. But then the exam would come around, and here's this problem that I've never seen before, and I would be stumped. I wouldn't even know where to begin. And it was because all I was doing to prepare was watching somebody else solve problems. I wasn't actually doing the work myself. I was really bad about doing my homework. And so that really kicked me in the teeth pretty hard. The way you really learn this stuff is by sitting down there and struggling and trying to see how things fit together in your head. You're learning how to organize that information for yourself, and you only get that by practice. So seriously, sit down, chug through some problems, that's the best way to do it. If you're watching videos, it's not really a very efficient use of your time, and it won't help you nearly as much as you want it to. It's a good supplement, but it shouldn't be like your main study course. All right, any other questions about that exam? Yeah, anything else that I can kind of clear up for you guys while we're talking about it?
No, that's it. Thank you.
Okay. Anybody else? All right. So, yeah, in terms of study guides, that's kind of the extent that I usually do. If there's a question you're particularly stumped on, now's the time to ask about it. I mean, obviously, if I ask it on the homework, I expect. What's that?
I have a question.
Yes, ma'am.
Okay, so I'm still doing a couple problems from homework 3 still because I just couldn't get them. Can you help me with 3.2?
Yeah, let's take a look at it real quick.
Yeah, 3.2. Because I just tried to do it and I don't get why I don't get what's not right.
Okay.
So basically, at first,
Let me pull the problem up just because I don't remember which one's which from memory.
It's 3.2, the homework.
Yeah, I'm saying I don't remember which ones they are. So I'm pulling it up on the screen now. All right, so this one, you have a plane that travels blah, blah, blah miles due east. Then a second leg of the trip, it travels some different number of miles southwest. And you want to find the magnitude of the plane's total displacement for the trip.
Yes.
All right. So what's going to happen if you're wondering, like, where does this fit in on that list of things for your exam? The place that fits in on the stuff that I want you to know for your exam?
Isn't it vectors?
Oh, yeah, it's definitely vectors.
But
specifically, it's the following things. This, actually, and even this. It's all three of these things. So that's what we're doing in that problem.
No, I know it's not the fact that I'm not. It's the fact that I'm not getting the right answer.
Okay, well let's figure out what do you so in your version of this problem, Anita, what's the first leg of that trip look like?
It's 470 miles east, and then 450.
Hold that thought. So the first part of that trip, we're going to go to the east, and I'm going to have, just like in a map, let's call east to the right. So yes. 470 miles. That's the first part of that trip. That is itself a vector. I'm going to call that vector A. Now, what was the second part?
The second part is 454 miles southwest.
Okay, so southwest on a map will be down and to the left.
I did you know when you did the grid,
like real quick.
454.
Right.
454. I basically put it on a graph.
You could. I mean, you could do this graphically.
So I can get the measurements, so I can know what to use the which measure to use the cosine and sine for.
And that's definitely what you would end up doing. So, for instance, like if I were putting this on a graph, I want to write this in vector notation. Well, this is purely in the x direction, but it's not in the y direction at all.
Yes.
So for vector A, all 470 miles is going to be in the x direction. So I could say that A equals 470 I hat, but 0 j hat. Remember, I, j, k, x, y, z. So when you see I hat, it means in the x direction. Now, what about vector B? Well, vector B is clearly to the west a little bit. So it's going to be something in the x direction and then also something in the y direction. However, it's to the left and it's down, so it's going to be negative something I hat and also negative something j hat. Does that make sense?
Okay.
Now, in this little triangle here, this angle right there is going to be a right angle by definition. But you do need to know what this angle is here. And the trick for that is that the problem said that it was southwest.
It's 45.
Yeah. Southwest is halfway between south and west, which means that's a 45-degree angle. They
Yeah.
could have said that it was like blah, blah, blah degrees south of west or west of south or something like that. And then it would have been some other angle. But yeah, so this will be 454 cosine 45. And that'll be 454 sine 45. How do I know which one is sine and cosine? Well, here's the x part, and it's the adjacent part of the triangle. And I remember that it's so So cosine is the adjacent side. And this right over here, the y part, was the sine because it's the opposite part.
I did that.
Okay.
So I did that, and then I got negative 321.0 for both. Well, no, you know what? No, yeah, for both. I got them for both, and then I subtracted them by 470. I had, and I got 149 minus 321, and then I tried to do the square root, but also like multiply, but also like times them by 2.
Time out. When you're doing the vector addition, you have to add the x parts to the x parts and the y parts to the y parts. Now in the x direction, you have two parts, positive 470 and negative 454 cosine of 45. When I do 470 plus this, I get positive 148.
Yeah, that's what I got 149, but yeah, same thing.
Right. Well, you said you got them both, but they're different, right? Your y component
No.
is going to be 0 plus
I
this, so it's
didn't
negative
mean it like
321.
that. I meant to say that basically when I wrote out what that B line that you have written out, I wrote the number twice. So I put minus.
Okay, I got you. I see what you're saying. I thought maybe you had the same components for both.
No. So I broke it down that way, and then that's how I was able to subtract it from the 470 to actually get 149. And then we had an extra the negative 321 because that's for the other side. Or do I need to do that twice?
No. This is it. This is your total right here.
So where did I go wrong?
Well, we're not done yet.
Okay.
Yeah, we're not done yet.
Maybe I just stopped.
This is your answer in component form.
Okay.
But the question asks you for the magnitude of the displacement.
I think that was the issue.
Yeah. So what's going to happen is, what's your total displacement look like? It's going to be this much to the right and this much down.
Okay.
So your total displacement is this diagonal. So this guy ended up going to the southeast by a certain amount. And how do I find that?
Square root it?
The square root of 148 squared plus 321
squared.
Yeah. And this is going to be the answer to the question.
Okay, so I did that, but I think I probably just did it wrong.
Could be.
Because I have the same thing that you wrote down, that you like have written down, like I squared it, but I probably just did the math wrong because I literally did all the steps that you just did. Okay.
Yeah, check. At that point, it sounds like maybe a bonehead math error or a calculator issue. Because
okay, at least I know I'm doing it right.
Yeah, the process is right. That's all there is to it.
Okay, I'll just try again.
Yeah. So one thing that I see some students do, this might be what's happening to you.
Yes.
Is when you have a negative number and you're squaring it, it's going to come out positive. But sometimes if you type in like minus blah, blah, blah squared, your calculator doesn't see that minus sign as the sign of the number. It sees it as an operation acting on the number. And it's going to use order of operations. So what might be happening is you might be taking negative 321, squaring the 321, and then subtracting that number from the other thing. And that'll give you an error.
Okay. Do I need to have my calculator on a certain mode or something? Because I had to reset it.
Well, if you're doing sines and cosines, you want to have your calculator in degrees mode, right?
Okay, let's make sure
Because
that's
the sine of 45 degrees is going to be the square root of 2 over 2. It's about 0.707. But if you
okay.
have your calculator in radians mode, then what's going to happen is the sine of 45 radians is like 0.85 something. It's like a whole different number. Because 45 radians is several trips around the circle, and I don't even know where you end up. That's not a number that is obvious to me on the face of it. So that's a trick that you might have to employ. One thing, if you work through some of these homework problems and you keep getting it wrong and you can't figure out why, after like the second or third time that you get it wrong, shoot me an email telling me that you're having an issue. Describe how you're doing the problem, and then move on to a different problem. At this point, most of them should be worked out, but it's not impossible for there to be a bug in the problems. One semester, when I ported the homeworks from one semester to the next semester, inexplicably the Canvas like ended up deleting all the answers for all the questions. It had the questions right, but all the correct answers in the list got zeroed out. So if you had typed in 0 for every question, it would have given you 100, even though it was not the answer to any of the questions. It was just a weird glitch, and I had to go back through and have it like recalculate all the correct answers in order for that to get fixed. There have been other times where I've made a typo when writing the question, and that caused the correct answer to be messed up. So if you can't figure out what's going wrong, it could be the problem is broken. I think most of those problems are fixed. I haven't noticed any this semester, but if you run into that, send me an email so I can go check to see if there's something wrong, and move on to other things so that you're not banging your head against the wall unnecessarily against a problem that you're just not going to get correct. All right.
Okay, thank you.
You're welcome. All right, any other questions about chapters 2 and 3? Do you guys feel like you have a sense of where we're going here? And
I'm gonna meet with you afterwards, like after hours.
Okay. Yeah, I know how you have a routine at this point. Any other questions? You guys feel good about that? Hopefully, maybe. Okay, I have no idea. All right. So at this point, we have done the concept of kinematics in its entirety. We've learned about how to describe objects that are moving. What we have not done is, hang on. All right. Well, so what's going to happen is we've learned how to describe objects of motion, but what we haven't learned how to do is to explain why the objects are moving the way that they're moving to begin with. Right? That's the part of kinematics that we call dynamics. So that's where we're going to start in chapter 4. We're going to learn why things are moving the way that they move. And what's going to happen is we're going to introduce what we call Newton's 3 laws of motion. I'm in class, sweetie.
But you're welcome.
Is this chapter 4?
It is chapter 4. Yes, we're starting chapter 4. And what I'm going to do is I'm just going to spell out Newton's 3 laws of motion. These are probably the most important things you're going to learn this semester. You should know them by heart. You should be super intimately familiar with these concepts. Yeah, I keep telling people that if I come to your 20th class reunion after you've graduated and I ask you what Newton's second law of motion is and you don't know the answer, we're going to take your degree away, right? That's how important this stuff is. And so let's just label them out. These were first proposed by Isaac Newton in his book Principia Mathematica. And they all deal with the way in which objects move. And what's going to happen is some of them are going to be perhaps a little bit counterintuitive, right? They're going to fly in the face of your expected experience. And so you're going to have to train yourself to think about moving objects a little bit more carefully than you have perhaps had to do in the past. So the first law of motion is also sometimes called the law of inertia. Right? And what it says is that an object tends to remain in motion at a constant velocity unless it's acted upon by a net force. Now, there's a lot of nuance packed into that one sentence. And in order to truly grasp all of that nuance, I want to point out some key phrases that contain a lot of that nuance. One is this phrase constant velocity. There's a lot packed into those two words. And if you're not careful, you're going to miss out on a lot of the information that's packed into those two words. The second is this phrase net force. I want you to concentrate on those two aspects of that law, because most of the meat of the law is going to come from those two sets of phrases. So when I say that something is moving with a constant velocity, it's important to remember what velocity means. What's the definition of velocity?
It's not the change in speed, because that's in the equation, but it has something to do with.
It has to do with change, but it's the change in what?
Position. Okay.
It's the change in position over time. It's the rate at which the position is changing. All right. And here's why that's important. All right. If you've got a constant velocity, that means that your position is changing by the same degree all the time. Right? So if you have a constant velocity, you can't be speeding up or slowing down, because then your rate of change would be going up or down. So constant velocity often means constant speed, but speed and velocity have a slightly different meaning as well. And so I can't replace this with constant speed and have it mean exactly the same thing, because what's the difference between speed and velocity?
I think the velocity have the magnitude and speed. Speed doesn't have magnitude.
That's right. That's right. When I say constant velocity, I don't just mean the speed. The speed is the number part. And certainly if you have a constant velocity, the number part will also be constant. So if you have a constant velocity, you for sure have a constant speed. But velocity is both the magnitude and also the direction, which means if I say an object tends to move at a constant velocity, it doesn't just mean at one speed. It means at one speed and also in one direction, right? So things want to move at one speed in a straight line. They don't want to speed up. They don't want to slow down. They don't want to turn. They naturally tend to travel at one speed in a straight line, according to the first law of motion, unless they're acted upon by a net force. So if there is not a net force acting on you, you're going to keep whatever velocity you have. You're going to keep moving in whatever velocity you've got in the same direction. You're not speeding up, slowing down, or turning. That's important. Notice sometimes when people cite the law of inertia, they'll say an object at rest tends to remain in rest and an object in motion tends to remain in motion. And I find that kind of redundant, right? Because if you are at rest, it means you have a velocity of 0. And if you have a velocity of 0, unless you're acted upon by a net force, your velocity will remain 0. So things that aren't currently moving aren't going to suddenly start moving unless there's a net force. Cool, that makes sense. Now, let's break down this second part. What do I mean by net force? Well, in order for me to parse what the heck a net force is, I should first have to figure out what a force is. What the heck's a force? If you ask Obi-Wan Kenobi, he would say it's an energy field created by all living things. It surrounds us and penetrates us and binds the galaxy together. But you guys probably aren't big Star Wars fans, so probably didn't know that. But in physics, that's not what a force is.
Mass times with the acceleration.
Close. We'll come back to that in a minute. But that's actually that's not a definition of what a force is. It tells me something about how forces work. We'll come back to that in a later moment. But a force is conceptually very simple. It's pushes and pulls, right? If I walk up to this pen and I push it, I can make it move, right? I'm pushing or pulling the pen, I'm exerting a force on it. So forces by themselves are just pushes and pulls. That's all there is to it. Now, a net force is a little trickier, right? What do I mean when I say net?
Total force?
Yeah, it's a total. And you got to be careful, though, because when you talk about net anything, you're adding a bunch of things together, but those things aren't always positive. Case in point, if I was a company and I was calculating my net profit during some quarter, right, what I would be doing is I would be adding up all the money that I take in, but I'd be subtracting out all the money that I paid out, right? So I'm adding a bunch of money together, but some of the money I'm taking in would be positive, and other bits of money, the money that I'm paying out, would be negative. So I'm adding things that are potentially positive with things that are potentially negative, which means it's possible to add a bunch of stuff and still end up with 0 because they all canceled, right? If I'm talking about, let's say the net weight of the box of cereal that I have on my shopping cart, what's going to happen is the net weight of that is going to be the weight of the entire box with all the stuff inside it minus the weight of just the packaging itself. So the idea is that they're telling me just the weight of the cereal inside without giving me the weight of all the plastic and cardboard packaging, right? So you're adding things together, but some of those things might be negative. The same thing is going to be true when it comes to forces. I could have pushes and pulls, but pushes and pulls are going to be vectors, right? I could push you to the right or I could pull you to the left. There's both a magnitude, that's how hard I'm pushing, and also a direction, that's what direction I'm pushing. And if they're vectors, I could have a push to the right and a push to the left. And one of those I might call positive, the other one I might call negative. And so the net force is what I get when I add those vectors together. So if I have a net force, that means that when I add all my forces together, I get something equal to not 0, right? If this force was really big to the right, but this force was really wimpy to the left, the net force would be something to the right. Whereas if they were both basically the same, the net force would equal 0. So that's what we mean by a net force. So the first law of motion says, if there isn't a net force, if all the forces add up to 0, my velocity will be constant. That's the big idea. And to some extent, that might be counterintuitive. It certainly was for the ancient Greeks. The ancient Greeks, they didn't get this concept. If you had asked Aristotle, he would have told you a theory of motion that is very, very wrong. He would have said, look, if I have like this pen and this pen is just sitting there, it has a natural tendency to remain at rest. Aristotle believed that things tended to remain at rest, and you could push them and they'd move for a while. Oh, I moved off screen, that was terrible. You could push them and they'd move for a while, but eventually they would return to their normal state of resting. And so according to Aristotle, if I wanted this pen to move, I would have had to keep pushing it. As soon as I stop pushing it, it's going to stop. Right? That's what they thought about stuff, but that's not what this says. According to this, once this pen starts to move, it wants to keep moving in a straight line at a constant velocity forever. So why is it that when I push my pen, within a second or so, it comes to a stop? If this is true, why did my pen stop?
Because there is another force act on.
Yeah. Yeah, as this pen slides across my paper here, there's a force. In this case, it's the force of friction as it rubs against the paper. And what's going to happen is that force causes its velocity to change and reduce itself down to zero, and that's why it stops eventually. Now, if I were to take the same pen and go out in the middle of a frozen lake where there's basically very little friction and give it a little kick, what would happen is it would slide a whole lot further. It would slow down a whole lot less. Now, even on a frozen lake, there's still a little bit of friction, and so it would still eventually come to a stop. But what if I were to take my pen and fly up on a rocket into deep, deep, deep interstellar space, far, far away from any sources of gravitation or objects, and give my little pen a push? Well, what would happen there is there wouldn't be any forces on it at all. And as a consequence, my pen would travel with one speed in one direction forever. All right, that's what the first law of motion says. So far, so good? The reason they call it the law of inertia is that that term inertia means resistance to change, right? When they say that, bureaucratic systems have a lot of inertia, what they mean is that they don't like to change. If I decide that I want to do things differently in the financial aid office, they're going to be like, no, we've used these paper forms for the last 50 years. We're going to keep using those same paper forms. So take all your newfangled technology and go away, because our 80-year-old secretary only knows one method and she's going to use that method. And it's like pulling teeth to get them to change stuff. That's inertia. And according to this, motion exhibits inertia. It doesn't want to change what it's doing. If you're already moving, you want to keep doing it. If you're not already moving, you don't want to start. That's the idea. Now, the second law of motion perhaps the most important of the three. It's going to tell us what happens if there is a net force. All right, the first law says if there's not a net force, my velocity will remain the same. The second law of motion is going to tell me, well, okay, if there is a net force, what happens? And I think Abigail already spoiled this on us, because what the second law of motion says is that the acceleration of an object, remember, acceleration is change in velocity. So if there's no net force, there's no acceleration. If there is a net force, there will be acceleration. It's going to tell us how much. It says the acceleration of an object is directly proportional to the net force, but inversely proportional to an object's mass. Now, as is often the case, you can say a concept in words, but mathematics is just another language. And sometimes it's a language that is considerably more concise and succinct. than annoying wordy stuff. But in order for us to understand how to translate this, I have to know what is meant by the phrase directly proportional and what is meant by the phrase inversely proportional. What do I mean when I say that two things are directly proportional? Well, two things are directly proportional if I can make the following statement. If I double how big one of them is, I will also double the other thing as well. So two things are directly proportional. If I double the net force, I will get double the acceleration. That's what it's saying. Now, by contrast, two things are inversely proportional. If I double one of the things, I won't double the other thing. I will, in fact, make it less. I'll make it half as big. So you double one, you cut the other one in half. You quadruple one, you cut the other one in fourths. So inversely proportional things, if one of them is bigger, the other one is smaller. Direct proportional things, if one of them is bigger, the other one is also bigger in the same manner. And what that means is that if I translate this statement, it says that the acceleration of an object is going to be related to the sum of the forces. This Greek letter sigma just means sum. So this is the net force per mass. And usually we rearrange this to write it to say that the sum of the forces on an object is equal to the mass of the object times the acceleration of the object. This is Newton's second law. And very frequently, I won't even write the sigma. You'll know from implication that the F we're talking about is not just one force, but the total of all the forces acting on the object. So this is the second law of motion. Now, this is useful to us because of two reasons, right? Reason number one is it helps us find the relationship between the net force and the mass. And reason number two is that it's the first time, between the net force and the acceleration, it's the first time that we've seen the term mass even show up in this class, right? We have yet to talk about mass, and this shows us where mass comes from, right? Mass ends up being a measure of the inertia of the object. Because what this says is that the more mass you have, the less you're going to accelerate for a given amount of force. If I have two objects with different masses and I push them both equally hard, the object with the larger mass is going to accelerate less than the object with the smaller mass, right? It's going to resist speeding up, slowing down, or turning more than the other object will. That's what mass is. Mass is a measure of how much an object doesn't want to change whatever its velocity is. Now, what's the SI unit of mass? Hopefully we all know this one.
Kilogram?
It is the kilogram. Notice it's not the gram, right? That's pretty weird. But until a few months ago, the definition of a kilogram was this particular piece of platinum iridium alloy in a vault in France. And so like if you wanted to have like a 1 kilogram mass, what you'd have to do is take your object, go to this vault in France, get them to pull this special thing out, measure them, see if they balanced. If yours was too heavy, you might drill a hole in yours to make them the same. And that's how you would determine like what 1 kilogram was we had this one standard. We said, that's a kilogram. We compare everything else to that same standard. Only a few months ago, I think it was like in the fall semester, this last semester, we redefined what a kilogram is. It's something different than it was a year ago. And now the kilogram is defined in terms of a particular experiment that we'll talk about next semester, because you have to know some electricity and magnetism to know how it works. but that's how we define it. So the kilogram is something different than it was when you were a kid. Who knew? But that is the standard definition of a kilogram. It's a measure of our inertia. Now, one thing that hopefully is clear then is if kilograms are measured in, or mass is measured in kilograms, and acceleration is measured in meters per second squared, what the heck are forces measured in? Well,
Newton?
well, yes, but what the heck's a Newton? Well, a Newton is going to be a kilogram times a meter per second squared. That is the SI unit of a Newton. And what that tells you is that if I have 1 Newton of force, that's how hard I'd have to push a 1 kilogram object in order to make that object accelerate by 1 meter per second every second. Right? That's what a Newton is. And you probably have thought about forces for years, but you probably don't use newtons as the go-to measurement for forces in your head. When you think about forces, you probably measure them in pounds, right? Pounds is the British imperial unit of force. And to give you a sense of how big a Newton is, about 9.8 newtons is the same thing as about 2.2 pounds. So 10 newtons is about 2 pounds. So 1 newton is about 1/5 of a pound of force, give or take. That gives you a sense of that. Usually at this point, I would hand around like a 1 kilogram mass that has a mass of 9.8 newtons, or has a weight of 9.8 newtons, just so you could get a sense of what 2.2 pounds was. But we're online, we can't do that. Nifty. So we've got that concept sort of locked down. One thing I should point out is that now that we know what mass is, I should probably address a similar but distinct quantity that is often confused with mass, and that is the concept of weight. Right? What the heck is weight? Well, weight is the force exerted on an object by gravity. And what's going to happen is people often confuse mass with weight. If you go to the grocery store and you take literally any box of cereal off the counter and you look in the bottom right corner of that box of cereal, it's going to say something like net weight, blah, blah, blah pounds, blah, blah, blah ounces, in parentheses, blah, blah, blah grams. Except grams are a unit of mass, not weight. Mass and weight are different things. Heck, if you look at Newton's second law that says F equals ma, well, you can see that, oh gosh, F is force, m is mass. They're two different things. Right? They can't be the same because they're not equal to each other. And in fact, when it comes to the force of gravity, well, what's going to happen is we know that from chapter 2, every object on Earth tends to accelerate by the same amount due to gravity. So even if I have a 100-pound object and a 1,000-pound object, gravity makes both things accelerate by the same amount. Now, according to this, the more mass you have, the less you're going to accelerate. So in order for the two objects to have the same acceleration, the only way that can work is if the force of gravity just happens to be way larger if you've got a bigger mass. So what's going to happen is the force that gravity exerts, your weight, tends to be equal to whatever the mass of the object is times g, the acceleration of gravity. And that's why if you have an object that's under the influence of gravity and nothing else, Well, the net force would just be this. So I'd have mg equals ma. And oh, look, if that's the case, the mass, since it's on both sides, conveniently cancels, and objects will have an acceleration equal to g. That's why that happens. So please, 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 when referring to mass and weight, try to use those terms correctly. It's one of my pet peeves when I hear someone say the word mass when they mean weight, or weight when they mean mass. It's like fingernails on a chalkboard for me, and it drives me crazy. So be careful about how you choose your words, because those two things, they're related to each other, but they are distinct. Why do we get them confused? Well, it's because we spend our entire lives living on the earth. And on the earth, if you know your mass, you're going to always know your weight as well. So that's why we tend to think they're kind of equivalent. If I have two things that have different masses, or have the same mass, they're going to have the same weight as well. But what's going to happen is not everything is on the earth. And the force exerted by gravity can change in different conditions. If I were to travel with a 1 kilogram object to the moon, when I get to the moon, the mass of that object hasn't changed. The mass of that object would still be 1 kilogram. But the weight of that object would no longer be 9.8 newtons. It would be about 1.67 newtons, because on the moon, gravity is wimpier. So your mass is the same no matter where you go. It will never change. It's an intrinsic property of that object. But your weight depends on the local gravitational characteristics of wherever you are. It's easy to forget that because we spend so much of our time in a place where gravity is essentially uniform. But weight can change, mass will not. So far, so good? So at this point, we have two laws of motion. The first one tells us that velocities tend to remain the same unless you're acted upon by a net force. The second one says, okay, well, if there is a net force, then my velocity will change, and it's going to tell me how much it will change by. And it turns out that the harder you push, the more it changes. The bigger your mass, the less it changes. That's the takeaway from the second law of motion. All right, one last law of motion. That's Newton's third law of motion. And it's probably another one of the ones that you probably know going in because you've heard it badly misquoted all over the place. So I'm going to try to quote this as rigorously as I can. It says that for every force on an object, that object I'll refer to as the push E, the one being pushed. There is an equal but opposite force on another object. Which I will refer to as the pusher. Right? For every force felt by an object, there's an equal but opposite force on another object. So this tells me two things. First, forces happen because two objects are interacting. You can't have a force unless there's a pusher and a push E, someone doing the pushing and someone getting pushed. Right? You've got to have two objects in order for there to be a force. So anytime you're trying to identify the forces that are acting in a situation, you should probably be asking yourself, who's the pusher and who's the push E? If you can't find the person or the thing doing the pushing, then maybe there's not really a force there and you're thinking about the problem poorly. The other thing that's important is that the forces that are on each of these two objects are equal but opposite. If I walk up and I push against the wall, I'm exerting a force on the wall. But according to this, the wall is pushing against me with literally the exact same force, but in the opposite direction. Right? If I were to, walk up and punch somebody, my fist is exerting a force on their face. Their face is exerting the exact same force on my fist. Right? If someone fires a pistol, then what's going to happen is there's a force pushing the bullet out of the gun in one direction. But if the gun is pushing the bullet one direction, the bullet is pushing the gun in the exact opposite direction, but with an equal amount of force, right? That's why there's a recoil when people fire guns, right? And that's universal. You hit a baseball with a bat. The baseball feels a force in one direction. The bat gets pushed back the other direction. Those forces are always exactly the same size, but opposite direction. Super easy. Now, what's going to happen is that's going to be useful when discussing motion, because quite frequently it's going to be important to know the forces on each object. Now, what's often screwed up by students when they're thinking about this is they forget that the two forces, these equal but opposite forces, they're not acting on the same object. So for instance, if I've got a box and there's a person pushing the box, right? The person pushing the box to the right, but the opposite force doesn't act on the box, it acts on the person. So this force acts on one object, the other force acts on the other object. We call them action-reaction pairs. So if I take this pen and I set it on the table, right? What are the forces that are acting on that pen? What's pushing the pen at this moment?
Nothing.
There's nothing pushing the pen at all?
Gravity force? Or
Yeah, gravity pulls on everything. So right now, gravity is pulling the pen downward. So why is the pen not falling?
the amount you pushing and then the gravity force balance it out?
Repeat that. I didn't catch that.
The amount you apply the force to the pen and then the amount the gravity are balanced out.
Well, but wait a second. I'm not touching the pen. What's actually pushing the pen right now? Bear in mind, you're looking down on the pen from above.
Of course, the gravity is pulling down, but the table have.
And that's what I'm looking for. It's touching the table, right? It's sitting on the table. So what's going to happen is, if this is my pen, there's gravity pulling it downward, and there's the table pushing it upward. And the reason that the pen isn't accelerating is because it just so happens that the table is pushing up just as hard as gravity is pushing down. Right? The net force acting on my pen was 0, and that's why it was stationary. Now, a lot of times students will look at a situation like this and they will mistakenly assume that these two forces are action-reaction pairs. Because in this particular case, this force and this force, they happen to be equal and they happen to be opposite. However, that's a misapplication of that idea. Because according to this third law, the action-reaction pairs will act on different objects. So what that means is that, for instance, the table is pushing the pen upward. But according to the third law of motion, if I were to look at the table is being pushed downward by the pen. It's being pushed downward a little extra hard, harder than it would be if the pen were not sitting on it, because this force and this force are equal but opposite. Does that make sense? But wait a second. The pen is being pulled downward by gravity. And according to the third law of motion, every force has a push E and a push R. So the pen is obviously the push E. It's being pushed or pulled by gravity downward. But what's the push R? What's the second object when I'm talking about the force of gravity?
Is it the air resistance applied?
No, because even if I had no air, there'd still be gravity, right? So it can't be air.
The friction force?
No, because even if I weren't like rubbing against anything, there would still be gravity. I don't need friction for gravity, so it can't be that either. Like, what's the object? Like, what's the thing doing the pulling?
The weight, I mean the mass of the object?
But when I say object, it should be a thing I should be able to point to, right? Objects are things I can literally see. What's the object? If someone walked up and punched me in the face and they said, hey, what was it that did the punch? I'd be like, it was that guy over there. That was the other object. But if I'm talking about gravity, hey, what is it that's dragging you down, Tom? I'd be like, what's the thing dragging me down? Gravity is this disembodied thing I can't point to, but it's a force being exerted by an object. What's the object?
The weight of the object?
The weight is not no. It should be a physical thing, a thing I can literally point to.
I don't know.
It's the planet Earth.
Oh God.
So what's going to happen is, in the case of gravity, right, the pen feels a force pulling it downward, but the pusher, the thing that's pulling it, is the literal planet Earth. However, according to the third law of motion, if the planet Earth is pulling the pen downward, it means that the entire planet Earth is being pulled upward by the pen. How come you don't notice that? If I take this pen and I drop it towards the ground, what I see is the pen fall toward the ground. I don't see the ground rise up to meet the pen. That seems weird. How come?
Because they use proportional force.
Because according to the second law, what's going to happen is the Earth is being pulled up just as hard as the pen is being pulled down. But the problem is the weight of this pen is not very big. It's not very heavy. And so what's going to happen is the force is pretty tiny. Now, for the pen, the force is tiny, but the mass is also tiny. And the acceleration that I get ends up being 9.8. It falls at 9.8. However, what about the Earth? Well, in the case of the Earth, the force that it's being pulled up with is the same tiny force that's the weight of the pen. However, the mass of the Earth is about 5.98 times 10 to the 24th kilograms. It is literally going to be a trillion times larger than the mass of this pen. But that means that same wimpy force divided by a trillion times bigger number is going to give me an acceleration that is a trillion times smaller. And as a consequence, it's so tiny we don't even notice it. So yeah, in principle, if you drop the pen, it should fall towards the Earth. The Earth should rise up to meet it, but it's going to move such a tiny amount, you wouldn't be able to notice it if you tried. Now, what if I pulled it with a much larger force? What if I was looking at the force of gravity between, say, the planet Earth and the sun? That happens to be the force that makes the Earth go around the sun, is that they are being bound by gravity. And in fact, what will happen is when the Earth's on one side of the sun moves a little bit toward it. When the Earth goes around the other side of the sun goes a little bit toward it. So one of the ways we detect exoplanets, but planets that orbit other stars, is we can watch that star, and even if we can't see the planet itself, sometimes we can detect the wobble in the position of the star, because as the planet moves around over here, it pulls the star this way. When it moves over here, it pulls the star this way. So we can watch it wobble back and forth. And from that, we can deduce that there are planets moving around them, right? Because for those, the size of the force was considerably larger. So even though the mass was incredibly big, it had a measurable acceleration. So that's the idea of action-reaction pairs. When we talk about forces, a big part of our job is going to be identifying what forces there are. And by and large, most forces that we're going to deal with are what we call contact forces. Right? Those are going to be interactions between a pushy and a pusher that are in direct contact. They're touching, right? The pen cannot feel a force from the table unless it is touching the table. When the pen is above the table, it feels nothing, right? Most forces will be contact forces. There are, however, certain forces that we call field forces. And field forces can act between two objects that aren't actually touching. The only field force we're going to talk about at all this semester is gravity. Every other force that we talk about this semester is going to be a contact force. So when you're trying to figure out what forces there are, Max, shut up. We're trying to figure out what forces they are. Should have had a cat. We're trying to figure out what forces there are. We're going to be asking ourselves what objects are touching the object of interest. If they're touching, they will be exerting forces. All right. I think we'll do some examples of how to put this stuff into practice next time, but I think that's enough for today. If there are any questions, have a good day, and may the force be with you.
I have a question.
Yeah.
It's not about the
I'm
homework.
sorry, I can't hear you over my dog.
Okay, the assignment, like it's assignments past due this
I
isn't
still can't hear you over the stupid. Max, shut up.
okay. The quiz we assigned to you is a due day at the day. Is that
Right,
right?
that's the pre-lab from last week.
Nope.
No.
Not pre-lab. It's hold on a second. Let me pull up.
I'm trying to figure out which assignment you're referring to.
Yeah, it's on.
Because what should be due today.
Okay, the 3.6 lunch angle, is that a due this morning or it's supposed to be like at night?
It's supposed to be midnight. That I may have missed the AM and PM switch for that one. I'll fix that.
Okay,
Yeah.
I think that's pretty much it.
But yeah, the stuff from two-dimensional motion should be due this evening.
Okay, perfect.
Yeah. So I'll fix that. Thank you for bringing it. If you see another one like that, please let me know.
Okay, I think that's what
I think it's the only one, or it would show up earlier on this list. But that was just I didn't end up changing that one when I changed the rest of them.
Okay.
So
Thank you.
yeah, you're very welcome. All right. So if there's no other questions, I will see you guys tomorrow.
Do you want to meet in a separate?
Yeah, we'll do it in my office hour room. I'm gonna kill this so it'll start processing the video of people who couldn't be here today.
Okay, thank you.
You're welcome, guys.